Ladies and gentlemen, what if the battery that was supposed to revolutionize electric vehicles is also the one quietly exposing the hardest truth about innovation? The 4680 cell was announced as a breakthrough that would cut costs, boost range, and redefine manufacturing. But behind the headlines lies a story of engineering friction, production bottlenecks, and a battle against physics itself. This isn't just about a battery. It's about what really happens when you try to reinvent an entire industry at scale, and why the most important breakthroughs don't arrive the way anyone expects. And when we introduced the 4680 battery cell at Tesla Incorporated, it wasn't positioned as a minor upgrade. It was presented as a fundamental rethinking of how batteries should be designed, manufactured, and integrated into vehicles. The 4680 form factor, 46 mm wide and 80 mm tall, was engineered to increase energy density, reduce cost per kilowatt-hour, and enable structural battery pack integration. The vision was bold. Fewer parts, simplified assembly, higher performance, and a dramatic acceleration toward sustainable energy. And so what is the disappointing truth? It's not that the technology failed. It's that scaling revolutionary technology is harder, slower, and more complex than most people expect. And the 4680 cell was designed to eliminate unnecessary complexity. By tabless architecture, we reduced internal resistance and improved thermal performance. By increasing cell size, we decreased the total number of cells needed in a pack, simplifying wiring and manufacturing. By making the battery pack structural, we removed redundant materials, allowing the pack itself to contribute to vehicle rigidity. On paper, and in controlled environments, the results were impressive. But manufacturing at global scale is a different challenge entirely. And producing millions of high-performance cells consistently requires extreme precision. Small variations in coating thickness, electrode alignment, or material purity can affect yield. Early production lines faced yield constraints. Scaling new dry electrode processes introduced complexities not fully visible in lab-scale environments. Equipment had to be redesigned. Processes had to be refined. Throughput had to increase without sacrificing quality. Each improvement required iteration. And that is the reality of innovation at scale. And another factor is cost optimization. The 4680 was expected to significantly reduce battery costs per kilowatt-hour. While progress has been made, the full cost advantages take time to realize. New production methods require upfront capital investment. New supply chains must mature. Raw material sourcing must stabilize. Achieving economies of scale is not instantaneous, it is incremental. And there's also the perception gap. When breakthrough technology is announced, expectations often accelerate faster than production capability. The market expects immediate transformation. Investors expect dramatic cost reductions overnight. Consumers expect major range improvements across every vehicle. But manufacturing revolutions unfold step by step. And in certain vehicles, early 4680 packs did not immediately deliver the dramatic range increases some anticipated. Improvements were targeted toward structural efficiency, manufacturability, and long-term scalability, rather than short-term headline numbers. The benefits are often more visible in production efficiency and vehicle architecture than in raw range metrics alone. And however, disappointment often stems from misunderstanding the strategy. The 4680 is not simply about adding more miles. It is about redesigning how vehicles are built. Fewer parts, lighter structures, faster assembly, reduced factory footprint, vertical integration, long-term cost reduction. These advantages compound over time. And at Gigafactory Texas and other production facilities, the ramp of 4680 manufacturing continues to improve. Each quarter brings better yields, improved equipment uptime, and process refinements. The learning curve is steep, but it is upward. And the broader mission remains unchanged. Accelerate the world's transition to sustainable energy. Battery innovation is central to that mission. The 4680 cell represents a platform shift. And platform shifts take patience. And the disappointing truth is not technological failure. It is that transformative innovation rarely follows a smooth trajectory. It involves iteration. It requires resilience. It demands long-term thinking over short-term optics. And when viewed through that lens, the 4680 is not a setback. It is a process, a long-term investment in manufacturing excellence, a step toward scalable energy storage not just for vehicles but for grid-scale applications. It reflects a philosophy of building the machine that builds the machine, prioritizing factory efficiency as much as product performance. And early challenges are data. Constraints are feedback. Every production obstacle becomes an engineering problem to solve, and solving those problems strengthens the system. And in high-volume manufacturing, perfection is not declared. It is earned through millions of cycles, refinements, and optimizations. The 4680 battery cell is part of that journey. Not a finished chapter, but an evolving system designed to improve over time through engineering discipline and relentless iteration. And in high-volume manufacturing, perfection is not declared. It is earned through millions of cycles, refinements, and optimizations. The 4680 battery cell is part of that journey. Not a finished chapter, but an evolving system designed to improve over time through engineering discipline and relentless iteration. And the deeper reality behind the 4680 program is that it represents vertical integration at a level rarely attempted in modern automotive manufacturing. Instead of relying entirely on external suppliers for critical cell production, the strategy has been to design, engineer, and scale cell manufacturing internally. That means building proprietary equipment, refining chemistry in-house, and controlling the production roadmap from raw material to finished pack. This level of control increases long-term advantage, but it also increases short-term complexity. And dry electrode processing, one of the most ambitious components of the 4680 strategy, illustrates this clearly. Traditional wet coating methods rely on solvents, energy-intensive drying, and extended production steps. The dry process promises lower energy consumption, smaller factory footprints, and lower operating costs. But implementing it at scale requires new machinery tolerances, new material behaviors, and new calibration systems. Translating laboratory feasibility into continuous high-speed production is not immediate. It demands thousands of incremental adjustments. And there is also the chemistry balance. Energy density, cycle life, charging speed, and cost must all coexist. Optimizing one variable can influence another. Increasing nickel content may raise energy density, but introduces supply chain volatility. Adjusting silicon content in anodes can improve performance but create expansion challenges. Every improvement must survive real-world testing across extreme climates, diverse charging patterns, and millions of miles of operation. And the 4680 cell was engineered not just as a standalone battery, but as a structural component. By integrating the pack directly into the vehicle's frame, overall mass can be reduced while improving rigidity. This enables simplified vehicle architecture, fewer components, and reduced manufacturing time. But structural integration means that battery consistency becomes even more critical. Variations that might be tolerable in a non-structural design become unacceptable in a structural one. Quality standards tighten. Inspection systems intensify. Precision increases. And scaling this across multiple factories adds another dimension. Lessons learned at Gigafactory Texas must be translated into processes that can operate reliably at Gigafactory Nevada and future facilities worldwide. Each location introduces new workforce training requirements, new environmental variables, and new supplier relationships. Consistency across global production lines is a systems engineering challenge as much as it is a battery challenge. And there is also the capital reality. Building advanced battery production lines requires billions in investment before full optimization is achieved. Equipment must be installed, tested, modified, and retested. Early output may not reflect long-term potential. Efficiency curves in manufacturing often follow a learning trajectory. Slow initial ramp, steady improvement, then acceleration as processes stabilize. Public perception often focuses on the early phase while the engineering focus remains on the slope of improvement. And another overlooked aspect is durability data. Large format cells behave differently than smaller cylindrical cells under long-term stress. Thermal propagation characteristics, charging gradients, and mechanical loads shift with scale. Extensive validation cycles are required to ensure safety and longevity meet internal standards. These cycles cannot be rushed without compromising reliability. And the market often compares immediate metrics, range, charging speed, cost per vehicle, without accounting for architectural shifts. The 4680 was never intended to be a simple drop-in replacement. It was designed to unlock manufacturing leverage. When a battery pack becomes part of the vehicle structure, stamping complexity changes. Assembly lines shorten. Material usage declines. These systemic gains compound over millions of vehicles. And innovation at this scale is rarely linear. Breakthroughs are followed by bottlenecks. Bottlenecks are followed by engineering redesigns. Redesigns unlock new throughput. Each constraint reveals the next improvement opportunity. The disappointing truth viewed narrowly is that revolutionary manufacturing cannot be accelerated purely by intention. It must follow physics, materials science, and process engineering realities. But the strategic direction remains intact. Continuous improvement is embedded into factory design. Data collection across production lines informs software updates and mechanical refinements. Automation increases. Scrap rates decline. Energy consumption per cell decreases. Over time, these incremental gains reshape the economics of electric vehicles. And battery innovation is not measured in weeks or quarters. It is measured in generational shifts. The 4680 cell reflects a commitment to long-term structural efficiency, scalable production, and vertical control over critical technology. The early challenges are part of the optimization curve inherent in transforming how energy storage is manufactured at global scale. And as production matures, the compounding effects become more visible. Simplified supply chains, faster assembly cycles, improved structural integration, and expanding capacity for energy storage applications beyond vehicles. Each refinement strengthens the foundation for the next phase of scaling, reinforcing a manufacturing ecosystem built to evolve rather than remain static. And as production matures, the compounding effects become more visible. Simplified supply chains, faster assembly cycles, improved structural integration, and expanding capacity for energy storage applications beyond vehicles. Each refinement strengthens the foundation for the next phase of scaling, reinforcing a manufacturing ecosystem built to evolve rather than remain static. And what often goes unrecognized is how deeply the 4680 program reshapes factory philosophy. Traditional automotive manufacturing optimizes around components sourced from multiple tiers of suppliers. The 4680 initiative pushes toward vertical compression. Fewer intermediaries, fewer transport steps, fewer redundancies. Cathode production, cell assembly, pack integration, and vehicle installation are increasingly synchronized. When synchronized effectively, this reduces cost variability and shortens feedback loops between engineering and production. And feedback loops are critical. Data from vehicles on the road informs material improvements. Production yield analytics guide equipment calibration. Thermal performance under extreme usage conditions feeds into software management updates. The 4680 cell is not isolated hardware. It exists within a digital ecosystem. Battery management systems continuously refine charging behavior. Firmware updates optimize efficiency. Over time, incremental software improvements unlock additional real-world performance without altering physical hardware. And there is also strategic resilience embedded in the design. Larger cell formats reduce the total number of cells required per vehicle. Fewer cells mean fewer weld points, fewer connectors, and fewer potential failure nodes. This simplification reduces assembly complexity and improves reliability at scale. While early production constraints limited output, the long-term architecture favors stability and throughput once optimization thresholds are crossed. And supply chain localization further reinforces this direction. Reducing dependency on long-distance material transport lowers exposure to geopolitical risk and logistics bottlenecks. Integrating material refinement closer to production sites improves predictability. These structural advantages are not immediately visible in quarterly metrics, but they compound over multi-year horizons. And another dimension of the 4680 strategy is energy density evolution. The physical format creates headroom for chemistry iteration. As cathode and anode materials improve, the larger format can absorb incremental density gains without redesigning the entire vehicle architecture. This creates a platform effect. Vehicles built around structural packs are positioned to benefit from chemistry upgrades over time. Engineering focus shifts from redesigning hardware to refining materials within a stable framework. And the perception of disappointment often centers on early-range comparisons between vehicles using previous generation cells and those using initial 4680 packs. Yet range is only one dimension of value. Structural packs reduce overall mass. Reduced mass improves efficiency. Improved efficiency lowers energy consumption per mile. Lower energy consumption reduces lifetime operating cost. These system-level interactions become clearer over extended ownership periods, rather than immediate specification sheets. And manufacturing automation also evolves alongside cell design. High-speed winding laser welding and precision inspection systems improve with each production cycle. Machine learning models detect anomalies earlier in the process. Scrap reduction directly lowers cost per kilowatt-hour. As yield improves from early stages to mature production, cost curves shift downward significantly. This dynamic is inherent in scaling new battery architecture. And workforce development plays a parallel role. Advanced cell manufacturing requires specialized technical skill. Training programs expand. Operational expertise compounds. Teams learn to anticipate equipment drift, material variance, and throughput constraints. Human experience integrates with automation, creating a hybrid system, optimized for consistency. And the structural pack architecture also influences crash safety engineering. By integrating the battery into the chassis, load paths are redistributed. Rigidity improves. Energy absorption zones are recalibrated. Safety validation becomes more complex, but long-term benefits include enhanced structural integrity and simplified underbody design. These improvements reflect a holistic approach, rather than isolated component enhancement. And energy storage beyond vehicles represents another strategic extension. Large-format cylindrical cells can inform stationary storage systems. Manufacturing efficiency achieved in vehicle cells influences grid-scale applications. Shared technology platforms reduce research duplication and accelerate overall energy transition efforts. And scaling globally introduces regional adaptation. Climate variations affect thermal management requirements. Charging infrastructure differences influence pack calibration. Continuous software refinement accommodates these regional variables without redesigning hardware. The 4680 program integrates hardware durability with software adaptability. And the broader context is industrial transformation. Battery production at this scale redefines factory design. Taller vertical integration, tighter production loops, and continuous iteration. Each solved constraint improves the system's resilience. Early inefficiencies are engineering data points guiding future optimization. And what appears disappointing in early comparison often represents groundwork for compounding improvement. Revolutionary architecture disrupts established processes. Disruption introduces friction. Friction drives refinement. Refinement produces durable advantage. The 4680 battery cell exists within that cycle of industrial evolution shaped by the realities of materials science, automation, supply chain engineering, and long-term scalability. And what appears disappointing in early comparison often represents groundwork for compounding improvement. Revolutionary architecture disrupts established processes. Disruption introduces friction. Friction drives refinement. Refinement produces durable advantage. The 4680 battery cell exists within that cycle of industrial evolution shaped by the realities of materials science, automation, supply chain engineering, and long-term scalability. And as iteration continues, the emphasis shifts from proving feasibility to optimizing throughput. Early production lines are designed with flexibility, allowing rapid modification of tooling, calibration, and material flow. Over time, those flexible systems transition into high-efficiency configurations once key variables stabilize. This progression mirrors the development of previous high-volume manufacturing breakthroughs. Initial variability followed by steady compression of tolerances and cycle times. And thermal management refinement is one area where long-term gains accumulate quietly. Larger cylindrical cells distribute heat differently compared to smaller formats. Cooling channel placement, coolant flow rates, and pack-level heat dissipation algorithms evolve with real-world telemetry. Each dataset improves predictive modeling. Better modeling reduces conservative buffers. Reduced buffers increase usable capacity. These incremental gains compound into measurable efficiency improvements without altering the external dimensions of the cell. And charging optimization follows a similar path. Fast charging performance depends on cell chemistry, internal resistance, and thermal stability. Early implementations prioritize longevity and safety margins. As confidence in production consistency grows, charging curves can be refined. Software-controlled ramp rates become more precise. Battery management systems adapt dynamically to temperature, state of charge, and usage history. This continuous calibration unlocks performance headroom over time. And material sourcing strategies also mature. Cathode supply agreements expand. Lithium refining capacity increases. Localized processing reduces transportation emissions and lead times. Vertical integration efforts inside Tesla incorporated strengthened control over cost variables. When raw material price volatility impacts global markets, internal efficiency improvements act as a counterbalance. And another dimension often overlooked is structural efficiency at the vehicle platform level. With structural packs integrated into casting-based architectures, part count declines significantly. Front and rear megacastings combine with the battery pack to form a simplified underbody. Fewer stamp components reduce weld points. Reduced weld points shorten assembly duration. Shorter assembly duration lowers factory energy consumption per vehicle. Each reduction cascades into cost stability, and manufacturing density within gigafactories continues to improve. Equipment layout becomes more compact as processes mature. Energy recovery systems capture waste heat. Automation sequencing reduces idle time between steps. Lessons from facilities like Gigafactory Texas inform improvements in future expansions. Replication becomes more efficient as design standards solidify, and yield improvement remains central. In early ramp phases, small percentage gains in yield translate into substantial cost shifts. Scrap reduction conserves materials. Process stability reduces rework. Advanced imaging systems detect electrode inconsistencies before final assembly. Each avoided defect protects margin and reinforces reliability. And long-term durability validation continues in parallel. Accelerated aging simulations replicate years of usage in compressed timeframes. Real-world fleet monitoring supplements laboratory data. Thermal cycling vibration stress and deep charge-discharge sequences refine degradation models. As predictive accuracy improves, warranty forecasting stabilizes, strengthening financial confidence in the architecture. And public expectations often prioritize visible performance metrics, yet internal engineering metrics focus on reproducibility and consistency. A battery cell that performs marginally better in ideal conditions but lacks production stability introduces systemic risk. The 4680 strategy prioritizes scalable consistency over isolated peak results. This philosophy aligns with the objective of producing millions of vehicles annually without sacrificing reliability. And energy density advancements continue through incremental chemistry tuning. Silicon content balancing in anodes evolves to manage expansion while enhancing capacity. Binder materials adapt to new stress profiles. Electrolyte formulations improve stability across temperature ranges. These micro-adjustments compound into meaningful improvements across production cycles. And global deployment strategy further amplifies long-term benefits. As cell output increases, more vehicle variants can transition to structural packs. Platform standardization simplifies design engineering for future models. Shared architecture reduces development time for new vehicles. Cross-compatibility enhances supply flexibility, and the broader energy ecosystem also benefits. Stationary storage products leverage insights from high-volume cylindrical production. Manufacturing automation applied in vehicle cells translates to grid storage scalability. Shared research accelerates both domains simultaneously, and innovation at this scale rarely unfolds with linear clarity. It advances through controlled experimentation, iterative correction, and disciplined scaling. Each constraint resolved strengthens system resilience. Each improvement reinforces manufacturing confidence. The 4680 battery cell continues to evolve within that framework, shaped not by short-term perception, but by sustained engineering refinement and structural integration designed for long-term global impact.